Hey everybody. So this is a unique research paper that caught my eye. Parallelized Planning Acting for Efficient LLM-based Multi-Agent Systems. And within this, it's a rather straightforward framework that you wouldn't think is unique, but it is actually unique knowing agent frameworks in and of themselves. So their framework is very straightforward overall, right? Essentially, what it is that they have a planning route and an acting route. And then you have multiple planners and multiple actors, and then just have them operate at the same time. And then kind of like counterintuitive to the human thought process, right? Which is we take a plan, and then we formulate a plan, and then we take action off of the plan. And then what this does is it just separates those like thought processes into two streams. So again, the planning stream and the acting stream, and just says, why not run both at the same time and run them concurrently, right? Very like again, like it's like simple logic, and then like I guess just like why not? Because the brain doesn't do it, and like that's the only reason. But when they do that, the researchers here are utilizing Minecraft as the benchmark, and then you'll notice like within a lot of AI research, Minecraft is like kind of it's used for a lot of benchmarks, right? Because it's easy for the model to go around and see how the model performs in different actions, etc. And then what they find is that like via this kind of a parallel processing method, the model is able to play Minecraft in a far better way, and essentially like it's able to solve like several areas of Minecraft like with 100% accuracy, is like the end result, right? That they're able to put out via this method. And then so doing what I do, I have played around with this method, and then taking a look at the code, and then building out the code. It's kind of it's straightforward what they do, right? So the first thing that I do is I build like this is a complete simulation. This first step is just fully 100% simulating the model and the architecture to understand how it works. And then so it just utilizes they utilize shared memory system. So between the all of the agents, they have shared memory. So that's cool. And between both of the channels, and then the observations and the action history are what updates the memory. And then it constantly is just retrieving the memories. And then you have your individual planning thread, and then your individual action thread, right? And then, but these are both operating simultaneously, and then so you're running them both and executing them both. And then you have either observations or no observation made, and that's kind of what's going on with the planning. And then based off of those in real time, it's taking actions. Yeah, in thread, which runs as well. And then the agents, right? And then so in this agent, in this instance, it's Agent Steve, and then he decides to attack based off of that simulation of the action. And then so this is like so step one is the parallelized planning acting system. Step two is the recursive task decomposition. So there's a skill library, right? And then the LLM model is getting access to all of this. So the LLM model gets access to this parallelized planning action system. It also gets access to this recursive task decomposition, which is a skill library. And then so this is like straightforward, right? Like if you've seen skill libraries before, especially within Minecraft, so it's like executing mine iron, Agent Steve executing action attack, executing collect wood, executing craft stick, Agent Steve executing action defend, executing craft pickaxe, executing mine diamond, etc. Right? And so it's just like the skills and like whatever skills are acquired and required for different actions, and that's kind of like how Minecraft works, right? So the model just keeps track of all of that within its memory. And then within all of that, the third thing that it does is it passes it all to a centralized memory system, and this stores team-wide observations, chat logs, and action history. So you have the planner thread and the agent thread, both are creating memories. Those memories go into the centralized memory system, and then they combine there, where both threads get access to the same, like the combined memories. And then so you can see this is the output of the combined memories, and then so it's just observation that Agent Steve found iron ore, Agent Alex is low health and retreating, chat logs, just restating that overall, and then so next thing I give you here is, let's say that you want to take this beyond a toy model and beyond the simulations, and you actually want to run this framework according to the research paper. Here it is for you. They use OpenAI in this instance, so I give you everything that you need in order to literally set up the exact same experiment that they ran here. I don't want to charge myself, so I'm not going to run it, but it's like a word-for-word recreation, basically, of their experiment, utilizing OpenAI and utilizing the OpenAI APIs, so you can recreate their exact experiments, but with lots of things on this channel, and then with lots of these algorithms as I go through it. This should have been a swarm algorithm, flat out, right? I take a look at what this is doing, especially with the parallelized nature of it, and the fact that they want like these multiple streams working together and working in conjunction together, much better as a swarm algorithm, where you essentially you create a class of action type, and then you have your actions, which would be move, collect, craft, combat, chat, explore, or build. And then you have your agents you go through, and then I'm utilizing pheromone-based deposits in this instance to get them to like do different actions, right? Interface, I want them to interact with the Minecraft environment, execute actions in the environment, etc. And then so I just need to map out all of the mathematics for that, right? And then so again, like swarm algorithms to map out all of that logic is not simple overall. I'm not going to state that. This is a lot of code in order to get this to run. But then once it runs, we can see like, so here's our agent Steve, right? And he takes all he's attacking, he's defending, he's mining, he's exploring. He does it all. And then agent Steve is like being controlled by individual swarm agents. And then these could all execute all at the same time, right? So it's all parallel process. Like these 100 actions or 50 actions that Steve takes could all happen right like that, right? All at the same time. Boom, it's all done, executed. All in parallel, which is exactly what this framework does and what they're providing here for you. And then so again, like you can run, I'll state it over and over again, right? You can run do 1,000 potatoes, but it doesn't mean that you should. And then so you can run this parallelized planning acting for efficient LLM-based multi-agents utilizing like thousands of dollars of OpenAI API, if that's what you want to do, by running this, or turn it into a swarm algorithm and then do it like the right way, right? Like potatoes versus tomatoes. And then so here you go. And if you like this type of content, please like and subscribe. Thank you very much.